Alright guys, welcome to the second video on equilibrium. This is talking about writing an equilibrium expression, which is based on something that we call the law of mass action. So what we're basically going to do here is we're basically going to turn reaction rates and rate laws into an expression that we can use to compare the reaction rates and figure out exactly where equilibrium is going to lie in a chemical process. All right, so again, we're going to keep going with our NO2 to N2O4 reaction. What I want to do though is we'll start actually working with some reaction rates. Right, so here's what we know. So we know that the rate of the forward reaction, right, so the direction from left to right, is equal to, well, we don't exactly know this yet, right, but we're going to make an assumption. We're going to assume that all reactions occur in one elementary step. Right? If you remember, the rate law for an elementary step is based on the coefficients of the things in that step. Right? So if we assume both forward and reaction occur in one step, we can write a rate law for this. So for our forward reaction, rate is equal to K for the forward reaction times concentration of the reactant, which in this case is NO2, and it's going to be squared because we have a 2 coefficient. Right, so that's the rate law for our forward reaction. We can also write one for the reverse reaction, right? So rate of the reverse reaction is going to be equal to K of the reverse reaction times the concentration of the reactant, or N2O4. This is just to the first power because our coefficient here is 1. Right, so these are our two reactions. Now what we know is that at equilibrium, we know that rate of the forward is equal to rate of the reverse. Right, so that's our given definition of equilibrium. So we're just going to set the two rate laws equal to each other. So the forward rate law is Kf concentration NO2 squared. And we're going to set that equal to the reverse reaction, which is going to be K reverse concentration N2O4. Now, an equilibrium expression, very simply put, is just going to be a ratio of these two things. Right, so we're going to talk about the ratio of the forward rate constant to the reverse rate constant. Right, so to do this, I just divide both sides by K reverse, and then divide both sides by NO2 squared, and I'm going to wind up with N2O4 over NO2 squared. So this is the ratio of the two rate laws. And this right here is going to equal something that we're going to in a second define as Q. All right, so all an equilibrium expression is going to be is just the ratios of their rate laws, nothing else. All right, so let's assume that we have a reaction. In this case, our equilibrium expression is going to be written the same way that we wrote the other expression. It's going to be written in the form Q is equal to products raised to their power over reactants raised to their power, right? So our actual expression is, I'm going to say Q is equal to concentration of C to the C power times concentration of D to the D power over A to the A power times B to the B power, right? So it's always going to be products over reactants. Each concentration gets raised to its coefficient as an exponent. Right, so this right here is the law of mass action. When you see a lot of these expressions, a lot of them are going to be written in terms of K. I'm using Q right now because Q is what happens at any given moment in time. right? So it is, like I say right here, it's a snapshot. So this is just comparing the concentrations of reactants and products at any point in time during the course of the reaction. All expressions are going to look like this, right? So anytime you have to write an expression, whether it be equilibrium expressions, which we'll use K, or these expressions right here, reaction quotients, which we'll use Q, will all be written exactly the same. All right, so a couple of important things. First thing is that in a law of mass action expression, solids and liquids are never included. Right? The reason why is that solids and liquids concentration is a function of their density. So it's not going to change as the reaction goes forward or backwards. So since it's not going to change, it's fairly constant. We just ignore them completely. Right? So no solids, no liquids ever in any type of expression of this manner. The other thing to keep in mind is that since pressure is proportional to concentration, you can also do an equilibrium expression using pressures of gases instead of concentrations. Now, you can only use pressure if everything in your equilibrium expression is a gas. Right? So if everything in that expression is a homogeneous gas, you can use pressure. Otherwise, use concentrations. Most things that you'll see will default to using concentration anyway. All right, so equilibrium expressions work the same way as Q expressions. The only difference is that you replace Q with K. All right, so if you are at equilibrium, or I'm going to have this as my next point, so I may as well just bring it up now. If you are at equilibrium, or if you are establishing an equilibrium, use K. If you're not sure whether you're at equilibrium at that point in time, use Q. Right, so Q is whenever the reaction's occurring. K is only for equilibrium, nothing else. The general forms we'll use are KEQ or KC. Those are our general constants. Right, so these will use concentrations most often. K sub P or Kp is going to be for pressures if you're working with gases. And this equation right here will let you convert between Kp and Kc, where what we have to remember is that delta N is the difference. So this is going to be change in the number of moles of gas. Right, so you calculate the number of moles of gas before, you calculate the number of moles after, you find the change, and that's what you plug in for delta N. Also keep in mind that because this is working with gases, the R we're going to use here is 0.0821 liter atmosphere per mole Kelvin. Right, so this is the version of R we're using here. This will actually become important because some of the equations I'm going to give you towards the end of this unit, we're going to use 8.314 as the version of R in those cases. Now, the AP exam nowadays will not ask you to calculate the difference between Kp and Kc. Right, so they're not going to ask you to convert between one and another. It's still something that's useful to know, especially for problems that we may come across in class. Now, as far as the actual value of K, what we need to work with is how large K is. Right, so if K is very, very large, so like the diagram we have here, if K is much bigger than 1, saying that equilibrium lies to the right means we're going to form significant amounts of products. Right, so we're going to have a lot more product than we'll have reactant the larger K is over 1. If K is less than 1, that means that the reaction is not product favored, it is reactant favored. So it will only react in the forward direction a little bit. So we'll say reactant favored, or you can say lies to the left. Now, one other thing to keep in mind is that if K is ridiculously huge, then we'll say the reaction is essentially it goes to completion, meaning you will have virtually no reactants remaining at the end. It doesn't go all the way to completion, but essentially it does because the products or the reactions you have left over are so minor they don't matter. Now, as far as some basic manipulations involving the equilibrium constant, there are 3 types of manipulation we have to work with. The first is if we're adding reactions. So, for example, if we're doing a Hess's law problem and they give us k for each individual step, all we do is we just multiply the k values whenever we're adding a reaction. If you are multiplying a reaction by a coefficient, so for example, if I were to do, if I did like NO2 to 1/2 N2O4, I know this isn't very realistic, but if we were to do this, then I would take whatever the K is for my reaction, and I would actually, so K, I'm going to call it K prime here for this reaction, is going to be equal to square root of K, because I'm going to raise it to 1/2, because I divided the first reaction from our example problems in half. And the other thing is, if you are reversing K, you just take the reciprocal. So if you're reversing the direction of the reaction, you just take the reciprocal of K. The K value that you have is for the reaction as written in a specific direction at a specific temperature. If you change the value, if you change the direction, do 1 over K. If you change the temperature, K is actually going to change on its own. Now, what we're going to do in the next video is we're actually going to go through and we're going to talk about some different types of problems or common problems that you'll see when you're working with equilibrium constants.